So biologists a lot of time have to deal with thick sample, so thick that it may not be suitable to generate informative results or high quality image. If you're using a regular fluorescent microscope, a light microscope, the sample is so thick that there are a lot of out of focus light coming from various layers of the cells that all reach the microscope and go through and reach the camera at the same time. And there is so much information that all you see is a blurry image. Blurry image is never good for microscopy, so we have to figure out a way to restrict our focus only to a single plane. And that is when we turn to confocal microscope, which allow biologists to be able to slice the sample into thin section, which at the end we can compile all those images together digitally. So the best analogy that you can think of is, imagine that you have a loaf of fruitcake, and if you are very interested in pinpointing the exact location in the three-dimensional space where each piece of fruit is located inside that loaf of cake, what you will have to do is to very thinly slice that cake, and the thinner you slice the cake, the more accurate the information is going to be. And at the end, if you put it together, now you have all the information you need to reconstruct the information that you're looking for. And that is what precisely confocal microscope help biologists do. The only difference is you obviously cannot slice a living organism into thin slices because you're going to kill them. And so confocal microscope allow us to do the slicing through a process called optical sectioning or optical slicing. So optical sectioning allows the confocal microscope to obtain the information from thin layer after thin layer of sections, and so that you can digitally reconstruct the image at the end. Now, how does a confocal microscope achieve that? It actually takes advantage of a very, very old trick called pinhole. Yes, that is the exact same pinhole that you use to create a pinhole camera when you are still in high school. In practice or in operation, the entire biological sample is actually illuminated from top to bottom. And as you can imagine, all the fluorescent molecule inside the biological sample, upon illumination, will emit its own fluorescent light. Now, with the pinhole, only the emitted light coming from that specific confocal layer will get through the pinhole and be registered as an image. Now, if you want to capture the entire volume of the 3D biological sample, it's very easy. Actually, all you have to do is to move the sample stage. Now, a different layer of the biological sample is now confocal with the pinhole. So upon moving up and down that sample stage, you can capture the entire height of the sample. Now the software can digitally put the entire 3D volume together, creating a confocal stack, which is your 3D data. So with modern technology, we can speed up that process very, very quickly. In fact, it is happening so fast that most biologists will be able to follow live biological processes as is happening inside a moving organism while being able to capture all the volumetric data and continue to make a 3D movie of a biological sample as life is happening. And so that is how confocal microscopy works.